Okay, welcome to lecture 4.6. Okay, here's where we left off. Okay, so if consumer J has to choose between transportation mode 1, 2, 3, 4, 5, or 6, bus, cab, so on, the modes we've denoted I. So the total loss from mode I is this term. Okay, now here's the choice that let's call it consumer J has. By the way, I haven't been using the J superscript. We're just going to pretend like we're just looking at one consumer for the moment. Okay, but now I'll say okay. Here's what. So we talked about the total loss, that term I just showed you. Let's call it TL sub I, the total loss from transportation mode I. And then what happens is, I'll call him consumer J. J chooses mode I if and only if TLI equals the minimum of TLK. Okay. So, K within big I. I'll call big I all the different modes of transportation. K within. I could do 1, 2, call it in modes of transportation, in total modes of transportation. So the key is, so remember this is a loss, and so they mix the mode of transportation that has the lowest loss. Now normally we might say we put the negative of the loss and call it utility, picks the mode with is the highest utility. It's the exact same problem. Okay, TL equals that. All right, now I'm going to come back to that. Here is the issue. Let me give you an anecdote, tell you a story. So Steve Levitt had so he graduated MIT. He took this 2-year postdoc at Harvard, and he's taken a job at University of Chicago, and he's becoming kind of famous for being like the guy on the economics of crime. And he wanted to start doing a project on the lethality of guns. Okay, and what he wanted to show is he had this idea that the reason, a big part of the reason guns cause so many deaths is not so much their lethality, but it's partly because of it's unclear who's the best at shooting someone. And his point was, in the old days before guns, uh, everyone solved disputes by fistfights. Okay, and if it were a fist fight, two people can just look at each other. Say it's two males. Two males look at each other, and the one who's bigger is probably going to win. And so the one who's smaller backs down. The problem with guns is you can't tell who's a better shot by just looking at someone. And so the problem is there's more uncertainty about who's going to win. And so therefore, if I have a gun and I'm up against someone else with a gun, I might not back down. I might think there's a good chance I could beat this guy because I can't tell how good a shot the other guy is. And because of that, the uncertainty about who would win in a fight, Steve hypothesized that causes more fights, or more lethal fights. And as a consequence, that's part of what's going on. It's the uncertainty about who wins that's causing all the killings. Surely the lethality also contributes to it, but it's partly just this the idea you don't know who's going to win. There's an old saying, Type Thomas Jefferson proclaimed all men are created equal. John Colt made it true. The idea is that, if you got a gun, John Colt has invented it. Even if you're small and weak, you got a chance of being able to kill or defeat someone who's bigger and stronger than you are. Okay, so that was the idea that Steve had. And by the way, this is what he told me. I don't even know if he did this paper. But here's what he was thinking of doing. The idea, the very simplest case would be, suppose that your strength in fighting or strength in shooting, your ability to win a fight, has to do with two factors: the scene factor. It's called person one. Suppose it's something like how big you are. That's your weight or your height, okay, which everyone can see. But then there's this uncertain term, this random term that only you know. If you're person one, only you know that term, okay. And then same thing. Suppose there's a person two, Z1, Z2, Z3. There's three people, and the person one might want to know what's the chance I'll win in a fight if I go up against person two and person three. Steve started off, he thought, okay, and I want to make this as simple as possible. What do I do? And he said, well, surely the best way to do this is to make these U's distributed uniform. That's the simplest distribution I can think of. And he said, each UI is distributed uniform. It's called 0A. What he wanted to do is look at this A if there's an aspect that's very unknown. So the idea is that with guns, A would be big, but with fistfights, A would be small. The key thing is the Z's. You can tell by the Z's. And he wanted to know things like, once he's done this, what's the probability? So probability that one would win in a fight. So you might want a probability Z1 plus U1 is greater than Z2 plus U2, and Z1 plus U1 is greater than Z3 plus U3. And this probability would equal, let's see, now the key is I'm going to go through some calculations. I'm going to just show you that even when you assume that it's uniform, that's the point I'm trying to make. You don't need to know the calculation I'm showing. The point I'm just making is this becomes a mess. Okay, so the next 2 minutes, that's the key point I want you, that's all I want you to get out of this is that this is a mess. Okay. You would start doing things like, if you want to know this, you might say, well, let's let U1, let's integrate it from 0 to A, and then given that we know U1, what's probability that Z1 plus U1 is greater than Z2 plus U2. So if we've given U1, so there's two random variables, U2 and U3, and we're assuming those are independent, so it's going to be probability that times probability Z1 plus U1 is greater than Z3 plus U3, and that equals the integral 0A times, it's going to be these terms like, I'm going to change that, probability U2 is less than Z2 minus Z1 plus U1 times probability of that second term. Now, when you start trying to figure out what is, say, this term, forget this term, the second term for a moment. This term is going to equal something like 0 if Z2 minus Z1 plus U1 is less than 0. It's going to equal Z2 minus Z1 minus U1 if that term is in 0A, and it's going to equal 1 if that term is greater than A. Okay. You see that all of a sudden this is a mess. That second term is going to be a similar term like that. Already, this is already a mess, and just with 3 people involved. And that's just to get the probability that Z1 wins in a fight. Then you might have some utility term where Z1 instigates the fight. You can see this is just going to become a mess, and Steve could see it. He's not getting anywhere. So what happened is Steve, so he's at Chicago, and he talks to James Heckman. James Heckman happens to be, I don't think he had won the Nobel Prize yet at the time, but he was the one who won he's an econometrician, won the Nobel Prize the same year that McFadden did. And Heckman told Levitt to do what I call the McFadden trick. Okay, I'm going to explain this in a second. The McFadden trick is to assume all of those random variables are distributed Weibull. Okay, and I'll explain in a second what that density or distribution looks like. But the key is it's some distribution. It's not uniform. It actually, at first glance, it looks like it's much more complicated than uniform. But it turns out it gives you a result that puts all these probabilities in a very simple, elegant manner. In particular, what it does is it says in that problem above, okay. So in fact, let's make it a total of instead of 3 people. Suppose J is within 1 to n. Okay, and then remember I said that your strength, whether you win a fight, had to do whether Zj plus Uj equals the maximum of all those Zj plus Uj. So let's call it sum over I within what's J? J wins if and only if equals max I within 1 to n n. Sorry, handwriting's gonna be bad. Zi plus ui. Okay. J wins if okay. Suppose each ui is distributed standard Weibull. Okay, and you know what? I thought I'd look this up. Extreme value type 1. Okay, so I'm going to call it is distributed standard Weibull, okay, or extreme value type 1. Okay, they're the same thing, or for my class, they're going to be the same thing. And I'm going to show you the distribution in a second, what the CDF looks like. McFadden calls it Weibull. He says it's assume all these error terms are distributed Weibull. There's a generational thing. It seems like, and I'm about the youngest of the ones who call it Weibull. And as I speak now, I'm 56, born in 64. Seems like about 53 is about the magic cutoff. Everyone younger than 53 calls it type 1, extreme value type 1. Okay. They're the same thing, so I'm going to stick with my generation, the older one. I'm going to call it Weibull. So assume each UI is distributed Weibull. Okay, then probability J wins. I'm going to call it probability J wins, which means that ZJ plus UJ is equals the maximum of all those. That probability is a very simple term, and I'm not going to prove it, but I want you to just memorize it. Okay, it equals E to the ZJ divided by the summation I equals 1 to N, capital N, E to the ZI. Okay, that's it. So in case where N equals 3, it's just, and then the probability, and then if J was person 1, it's just E to the Z1 divided by E to the Z1 plus E to the Z2 plus E to the Z3. By the way, so you should be able to see, if instead we want to know the probability that 2 wins, it's just E to the Z2 divided by that denominator. If we want probability that 3 wins, it's E to the Z3 divided by that denominator. And you should be able to see very quickly that those 3 probabilities have to sum to 1. Okay? So I want you to memorize this. So with that, what I call the Weibull, the McFadden trick. Okay? So if you want the probability that some term is the maximum over a set of, say, n terms, what you do, assume the error term for each of them is distributed standard Weibull. Okay, some students have asked me, why are you assuming Weibull? The answer is because that's what makes it easy. Okay, it's not because we think there's truth to it, or it's otherwise the problem is just a mess. This is what makes the problem solvable. Okay, so if we assume that all the U's all the error terms are distributed standard Weibull, the probability that any person J wins is just E to J's seen utility. So that's what we have here. Is we have if it was a choice, and this is utilities, ZJ's the seen utility, what all the researchers see, I guess all the other people that involved, plus the unseen utility. Okay, in the Levitt problem, it's your seen ability, how big you are, plus your unseen ability, possibly how good you are at shooting. Okay, or the gumption in you, how good you are at fist fights, something it could be. But the key thing is you look at, to calculate those probabilities, you look at the seen terms, the terms that are known to the researcher. These are the ZJs in this case, so it's E to the Z1 divided by that. Okay, that is, that's how you get the probability. So that in turn, so let's see, what do I want to do? You know what? I'm going to stop there. I've gone almost 20 minutes. So let me explain that Levitt story. Now I'm going to use that Levitt / the Heckman advice, go back to the McFadden problem, and we're going to fill in the next of our recipe. So we're going to talk about the probability that consumer J chooses BART, probability consumer J chooses bus, and so on. Okay, and that will be, let's see, this is 4.6. Okay, so we'll see you there in 4.7.